Today we're going to go over the Bronsted acids and bases, the conjugate acids and bases, and pH. So, what is an acid-base reaction? Well, it's fundamentally the reaction of a proton H+ transfer. The transfer is usually very fast in water, so it reaches equilibrium quickly. Acid-base reactions are a good example of the application of equilibrium concepts. Very important in water, plays an essential role in determining the structure and interactions in water of biological molecules. Now let's look at the older definition of Arrhenius' definition of an acid and a base. The acids are acids that produce hydronium in water. So for an example, we have hydrochloric acid with water forming chlorine ion and hydronium. Well, the hydrogen comes off of the hydrochloric and forms hydronium by adding the hydrogen to the water. So that means hydrochloric acid is your acid while your water is your base. Now for the base, it produces hydroxide in water. For example, we have ammonia with water forming ammonium and hydroxide. The hydrogen comes off of the water to form ammonia. So because the hydrogen is coming off of the water is our acid and our ammonia is our base, based off of this definition. And because the hydrogen comes off of the water, it forms the hydroxide. Now, a better definition is the Bronsted definition, or known as the Bronsted-Lowry definition. There are limitations of the Arrhenius definition. Many substances that yield the hydroxide ions in water do not contain the hydroxide in their formula. Examples: ammonia, the amines, and many salts of weak acids such as sodium fluoride. Another limitation is that water had to be the solvent for acid-base reactions, which isn't always the case. So for the Bronsted definition, the acid is a compound that donates the hydrogen proton to another compound. For base, it's a compound that accepts a hydrogen proton from another compound. And the acid-base reaction just means the transfer of the hydrogen proton from an acid to a base. So as you can see, when I was doing the ammonia to make ammonium, I actually was looking at the Bronsted definition because the Arrhenius definition just didn't make sense. One thing to note is water is amphiphoritic. That means it acts as a base, which means it accepts a proton in one case, and it acts as an acid, donates a proton in the other. Now let's go on to conjugate acid-base pairs. So the Bronsted definition provides a new way to look at an acid-base reaction, because it focuses on the reactant and the products as acids and bases. Every acid has a conjugate base, and every base has a conjugate acid. The conjugate base has one fewer hydrogen and one more minus charge than the acid, while the conjugate acid has one more hydrogen and one less minus charge than the base. Let's take a look at some examples. Alright, so let's take a look at ammonia, acetic acid, forming ammonium and the acetate. So one thing we notice is the hydrogen comes off of the acetic acid and forms onto the ammonia to give us ammonium. So that means because the acetic acid is the one that's donating the hydrogen or the proton, it is known as our acid, while our ammonia is the one that is accepting the proton, so it's our base. Now for conjugate acids and bases, we just need to look at the product side. So our acetic acid, the opposite of it, as you can see, has one less hydrogen to it and has one more negative charge, so it is now the base. while for the ammonium, it has one more hydrogen to it and one less negative charge, so it is known as the acid. So when we write this out, we have NH3 as the base with a conjugate acid of NH4+. For the acetic acid, we have C2H4O is our acid, while its conjugate base gives us C2H3O negative. So this is what we mean by conjugate acid and conjugate base. So when we go from our conjugate acid, we subtract a hydrogen or a proton to get us our conjugate base. Well, if we go from the base to our conjugate acid, we are adding a hydrogen to the acid to form the acid. Let's take a look at some more examples. If I was given HCl, what would be its conjugate base? Well, for conjugate base, I need to have one less hydrogen and more negative charge. So it would be chlorine ion. For water, what is its conjugate base? I need one less hydrogen, so OH, and a negative charge. So we get hydroxide. Let's take a look at H2SO4, sulfate. And what is its conjugate base? Well, I need one less hydrogen and a negative charge. Now let's take this product and let's find the other conjugate base, because we can keep going because we have more hydrogens. So we have HSO4 negative, and its conjugate base again is taking away one hydrogen and adding more negative charge. So we get sulfate. So we can also talk about acid-base strength and the net direction of the reaction. So a reaction proceeds to the greater extent in the direction in which a stronger acid and a stronger base form a weaker acid and a weaker base. So if we look at this chart, we can see what our strong acids are right here. And if we go down, we can see our strong bases. So one thing you want to remember is our strong acids will have a negligible base, our weak acids will have a weak base, and our strong bases will have a negligible acid. So again, let's take a look at the chart, and we can see that. So our hydrochloric acid, for example, is a strong acid, but its base is negligible, chlorine minus. Now let's take a look at our weaks. So let's look at phosphoric acid and its conjugate base. And if you notice, we still have a weak acid going into a weak base. Now let's determine our K. Is it going to be greater than 1 or less than 1? And we're going to be using this chart. This chart can be found on page 790 of your book. Alright, so let's take a look at this example. So first we're going to identify our acids and our bases. So we need to look at our conjugates. So if we notice here, our hydrogen is being pulled off from this to form hydronium. So that means this molecule right here needs to be labeled as our acid. And its conjugate, of course, is a base. So because this molecule is our acid, that means the water needs to be our base, and hydronium is the acid. Next, we need to label which one's stronger and which one's weaker. Well, this molecule right here isn't in your chart, so one way of doing this is to look at the bases and to see which one has the most hydrogens to it. The one with the most hydrogens will usually be the most stronger. So that means this side, because the water molecule has more hydrogens to it, this side is the stronger side, while this side, the products, are the weaker. So that means our K is greater than 1. Let's do another example. Alright, so let's take a look at this example. First thing we're going to do is identify which ones are acids and which ones are bases. So here we go. So if we look at our molecule here and our molecule here, we notice that a hydrogen or proton was donated. So that means this molecule is our acid. So we're going to label it. Now on the product side, that means this molecule is our base. Looking back at the reactants, because we have our acid, that means ammonia needs to be our base. And that in the product side, ammonium is the acid, the conjugated acid. Now we need to figure out, well, which one's stronger. So again, I'm just going to look at the bases, and I'm going to look on the chart on page 790. Because NH3 is the stronger base than HPO42-, that means this side is stronger, and this side is weaker, and our K is going to be greater than 1. Let's do one more example. So we have this formula. Now the first thing we're going to do is figure out which ones are acid and which ones are bases. So here we can see we have hydrofluoric acid, and then on the product side it's just a fluorine. So that means that hydrogen was donated to the hydronium. So our hydrofluoric is going to be our acid. That means the fluorine is our conjugate base. Our water is going to be our base, while our hydronium is going to be our acid. Now we need to figure out which of the bases is stronger. Is it the fluorine or is it the water? So we're going to take a look at the table on page 790. One thing we notice is fluorine is stronger than water. So that means this side is stronger, the product side, than the reactant side, which is weaker. So that means our K is less than 1. So one thing you want to note here is the stronger the acid, the weaker its conjugate base is going to be. And again, you can take a look at figure 18.8 on page 790 in your book to take a look at this trend. So now let's take a look at chapter 18.2, pH. So let's talk about autoionization of water, aka self-ionization. So when we have two water molecules, what happens is the lone pair of oxygen binds to the H+. So this lone pair right here binds to this H+, and it pops off this hydrogen. So what we form is hydronium and hydroxide when water autoionizes. So like any equilibrium process, the autoionization of water is described quantitatively by an equilibrium constant, and this is known as K, which is the equilibrium constant, W referring to water, and it gives us H3O plus OH minus. Now we don't add these two water molecules. Why? Because it's in liquid form. That means it's a pure liquid. So it doesn't get added to anything of an equilibrium constant. Now one thing we do need to know is that Kw is equal to 1.00 times 10 to the minus 14th at 25 Celsius. Now this is very important to remember, and it's an equation you will need to know. Now in pure water we find that hydronium is equal to hydroxide, which means the 1.00 times 10 to the minus 14th, if we square root it, we get 1.00 times 10 to the minus 7th at 25 Celsius, the molarity for hydroxide and for hydronium. So you will need to memorize that hydroxide is equal to 1.00 times 10 to the minus 7th molarity, or the pH is equal to 7, and hydroxide is equal to 1.00 times 10 to the minus 7th molar, or the pH is equal to 7. Now, how did I get this pH number? Well, I used the equation pH is equal to the negative log of, let's say, hydronium for right now. So I plug in this number and I get 7. I can do the same thing for the pOH, which equals to the negative log of hydroxide, which will give me 7. OH refers to bases, while the H refers to acids. So when we add acid to water, for example, we have HA, which refers to acid. Water forms A- plus hydronium. We find out that hydronium is greater than 1.00 times 10 to the minus 7th. Also, it tells us our pH level is going to be less than 7. So our acids are normally smaller, usually 1 to 6.9. Now for the base, OH minus, it's going to be less than 1.0 times 10 to the minus 7th, and that means our pH is going to be greater than 7. So anything 7.1 and above is very basic. Now what happens when we put base in water? So the equation would go, our base plus our water is going to form our conjugate acid plus hydroxide. Well, what we find is our hydroxide, OH minus, is going to be greater than 1.00 times 10 to the minus 7th, or pH is going to be less than 7. Now for our acid, our hydronium, it's going to be less than 1.00 times 10 to the minus 7th, but the pH, OH, is going to be greater than 7. Sorry, this should be pOH right there. So our pOH would be less than 7 for our base, and our pOH would be greater than 7 for our acid. So let's talk about the pH scale. In aqueous solutions, hydronium can vary from about 10 molar to 10 to the minus 15 molar. To handle numbers with negative exponents more conveniently in calculations, we convert them to positive numbers using a numerical system called a p-scale. So pH is equal to the negative log of the hydronium. To find the hydronium from the pH, you perform the opposite arithmetic process. So our hydronium is equal to 10 to the root minus pH. A p-scale is used to express other quantities as well. So to find the base, the pOH, you can use negative log of the hydroxide. If we're looking for the equilibrium constant, the pK, we can find the negative log of that equilibrium constant to find its pK. So we can also see relationships among pH, pOH, and pKw. So if we know that Kw is equal to hydronium and the hydroxide, and it's equal to 1.00 times 10 to the minus 14th, we can now take the logs of all of these. So the negative log of Kw is equal to the negative log of hydronium times the negative log of hydroxide, which gives us the negative log of 1.00 times 10 to the minus 14th. This gives us pKw is equal to pH plus pOH, which equals to 14. So for logs, the number of significant figures is going to equal the number of places to the right of the decimal point. So we're going to see that when we work out a few problems. So let's do a few problems so you can understand how we go from pH to hydronium, hydronium to pH, hydroxide to pOH, and pOH to hydroxide. So for given the equation, what is the pH and pOH of a solution in which hydronium is equal to 5.75 times 10 to the minus 4 molar? First thing you need to realize is we're working with hydronium. So the first equation we can only use is to find the pH. We can't use the pOH because this is not a base, it's an acid. So our first equation is going to find the pH. So pH is equal to the negative log of hydronium. So when we plug in that number, we're going to get 3.240. Now here's where the sig figs come into play. As you can see, we have 3 significant figures for the molarity. Well, for the pH, you need to have the same amount of significant figures after the decimal. So you need to have 3 significant figures for the pH. Now for the pOH. So because we know the equation, pKw is equal to pH plus pOH, which equals to 14.000. This is a known number, so it doesn't matter when we're looking for sig figs. We can plug in to find pOH is equal to 14 minus pH to give us pOH is equal to 10.756. So again, we need to have 3 significant figures after the decimal point. Why? This number here is a known number. So it can have as many significant figures after the decimal point as needed. But this is the number we were looking for sig figs, as well as this number. Now let's do another equation. So now we're going to find what is the hydronium and the hydroxide of a pH of 10.72 solution. Alright, first we need to remember that this is an acid, so we can only go from the acid to an acid, not from an acid to a base. Alright, so the first thing we're going to do is we're going to find the hydronium using H3O plus equals 10 to the minus pH. So we're going to plug that in, and we're going to get 1.9 times 10 to the minus 11th molarity. Remember, hydronium and the hydroxide are molarities. Now, why do I have 2 significant figures? Well, because I had 2 significant figures after the decimal point. That means my molarity needs to be 2 significant figures. So now that we have hydronium, we can now find the hydroxide. We're going to be using the equation H3O plus OH minus is equal to 1.00 times 10 to the minus 14th molar. and we get hydroxide is equal to 5.3 times 10 to the minus 4 molar. And again, it's going to be two significant figures. So to make a better note for sig figs, when you have pH, and let's say we had 3.28, we're going to be looking at after the decimal. So when we have hydronium, we're looking at the full number, which will be right here. So if our molarity has a full 2 sig figs, then our pH needs 2 figs after the decimal point. Alright, for your assignment, I want you to read chapters 18, going from sections 3 to 1. The problems are in chapter 18, 43, 45, 47, 51, 55, 57, 27, and 29. These can be found at the back of that chapter. And then if you go to the Chem 201 website, click on PS number 3 handout, I want you to work on that as well.